This ionic bond also called a electrovalent bond. Now here no bond is no compound is 100% ionic in nature. Means here there is no 100% ionic in nature. There is some amount of covalent nature also present in ionic compounds. Some covalent nature also present in such compounds. Already one point explained to you, the electronegativity difference is greater than 1.7, that is ionic in nature, ionic compound. Electronegativity difference between two atoms is less than 1.7, that is generally covalent in nature. Now that electronegativity difference is equals to 1.7, 50% ionic and remaining 50% covalent in nature. This is covalent compound. Based on their electronegativities, here based on their electronegativity difference between two atom formats present in a compound, we can explain its ionic covalent or 50% ionic and covalent in nature. Okay. Now, based on Fajans rule, to explain the nature of a bond, either maybe a covalent bond or ionic bond, here we want one important definition, that is polarizing power or polarizing ability. Here polarizing ability of cations, particularly we can use for cations to express ionic or covalent character. Polarizing power of a cation, it is the ability of a cation to polarize nearby anions is called a polarizing power or polarizing ability. Now that polarizing power to cation is directly proportional to charge on cation and inversely proportional to the size of cation. This is very, very important. The next one is polarizability. This is polarizing power. This is polarizability. This is the tendency of an anion to distorted by cation is called your polarizability. Now that polarizability to anion is directly proportional to the charge on anion and also directly proportional to the size of anion. So based on these polarizing power and polarizability of cations and anions, we can easily express the nature of ionic or covalent nature. Here, based on this polarizing power and polarizability of cations and anions here, this polarizing power generally we can use for cation, particularly charge directly proportional and inversely proportional to the size of cation. Polarizability is related to the anion. Both are directly proportional, charge and size. Okay. So based on this, one important note point is here. Yeah, the PP polarizing power is increases covalent character also increases. Your first point is polarizing power increases, covalent character also increases, means this is increases. To increase the polarizing power, charge on cation is more and the size of the cation is less. Now, generally here polarizing power PP generally means charge on the cation PP increases from left to right in the periodic table. Here polarizing power PP decreases, polarizing power decreases, this polarizing power decreases because size of the cation increases from top to bottom. This is top to bottom in the periodic table. Next one is polarizability. Your polarizability generally means charge on here it is left to right anion polarizability decreases and here the top to bottom increases. By using these important points, we can easily explain its nature, ionic or covalent nature. Very, very important concept for objective. This is. Now here, Fajans created Fajans rule based on this. Fajans rule for a given anion, means anion is same, the size of cation increases, covalent character, what happens? Covalent character decreases. Very, very important concept. Fajans created. For a given anion means I'll take LIF, NAF, your KF, your RBF, and CSEF. For a given anion means your anion F minus, F minus, F minus, your F minus. In all cases, fluoride ion is common. That's why for a given anion, the size of cation increases. Covalent character, what happens? Decreases. So among these, which is more covalent means here the LIF is more covalent because Li plus 1, Na plus 1, K plus 1, Rb plus 1, Cs plus 1. So are the cation means lithium ion, sodium ion, potassium ion, rubidium and cesium ion. Size is more for cesium. According to this polarizing power, charge on cation is same +1, +1, +1. We can see the size of cation. Size of cation increase, polarizing power what happens? Decreases. When our polarizing power decreases, covalent character decreases, ionic character increases. Relation. See here, polarizing power increases, covalent character also increases. But here size increases, polarizing power decreases, covalent character also decreases. That's why among the given options, lithium fluoride, sodium fluoride, potassium fluoride, rubidium fluoride, and cesium fluoride, which is more covalent, I mean this is the more covalent. This is more covalent means least ionic in nature. But CSF is more ionic, this is more ionic in nature. That is one of the most important principle or point of Fajans rule. Similarly, for a given cation, one of the most important Fajans rule for same cation, for a given same cation is same, the size and charge, the size and charge of anion increases, your covalent character also increases. Covalent character also increases. See here, for a given cation means I'll take sodium fluoride, sodium chloride, sodium bromide, sodium iodide. This is cation is same, Na plus, Na plus, Na plus and Na plus. Cation is same. But anion here F minus, Cl minus, Br minus and I minus. Now this is the F minus fluoride, chloride, bromide and iodide ion. Here we can use charge is the same. Here charges remains constant, but size what happens? Increases. Because F minus, Cl minus, Br minus, I minus, top to bottom these halide ions size increases. That's why polarizing power increase, covalent character also increases. So among these, which is more covalent means here NaI is more covalent in nature. Because for a given cation is same, the size of anion increases because polarizability is directly proportional to charge and size. Your covalent character also increases. That's why it is means less covalent in nature. Less covalent. Less covalent means it is more ionic in nature. Now here this is more covalent. More covalent in nature, it is less ionic in nature. Based on this only, in 2019 NEET examination, one question created based on this. So, based on this, in 2019 NEET examination, one question created. I'll explain that. So here, based on this, if you have material, see the question number 53. Yeah, which of the following is incorrect statement? Which is incorrect statement? This is 2019 now, a neat question. First one is PbF4 is covalent in nature given. Covalent in nature. Second one is SiCl4 is easily hydrolyzed. Third one is GeX4, that X is fluorine, chlorine, bromine, and iodine, is more stable, than GeX2. And fourth one is SnF4 is ionic in nature. These are the four important points, four important options created. So which of the following statement is incorrect? Once we can observe here among these four options, first one is incorrect according to this concept. For a given same, we can consider for a given same cation like NaF, I will take PbF4, PbCl4, PbBr4, and here the PbI4. Here the charge is +4, +4, +4, +4. Charge of cation is +4 lead. But all the anions -1, -1, -1, -1. For a given same cation, here the size of the anion increases, covalent character increases according to Fajans rule. Now, statement is given. This is given statement is this is PbF4 is covalent in nature. But here, according to the statement, the size of anion compared to the fluoride ion, iodide ion size is more, covalent character is more. That's why increasing order of their covalent nature is like this. But while comparing these four compounds, it is generally PbF4 is ionic in nature, more ionic it is, more ionic. It is covalent in nature. But statement given PbF4 is covalent. That is incorrect statement. That's why this is the correct answer. That's why in chemical bonding, better you read a line to line synopsis, and based on like a very simple points they'll create one question based on their bonds. That's why I'll give the complete synopsis clearly and follow the all previous year questions as well as levels. Will get clear information and guarantee will answer for a given 3 questions without any mistakes. 12 marks will get it from this. Thermodynamics 2 questions. Already in physics started, sir. Both in thermodynamics and physics and chemistry, nearly will get in chemistry 2 questions, 8 marks, and here 12 marks, 20 marks out of 180 from 2 chapters. So read thoroughly. Then here second option in this question, SiCl4 is easily hydrolyzed, means SiCl4s, it is not correct. That is it is not wrong answer, it is correct answer only, because SiCl4 reacted with the water easily hydrolyze, it forms SiCl2OH taken twice plus 2HCl is formed. In first year, in p block elements carbon family to prepare silicones. Yeah, the silicon tetrachloride is reacted with water, will get like this, and also these are reacted with alkyl halide, will get like this. Si, yeah, the Cl and your Cl, OH and your OH. This is easily hydrolyzed. Then third one is XeF4 is more stable than XeF2. It is more stable than compared to this, because for third option, why it is more stable means here the Xe GX4, here the oxidation state is +4, and here the GeX2 +2 oxidation state. In this compound, the size of xenon, germanium size is less than compared to this. Now, here the size of germanium +4 is less than germanium +2. Based on this, this is more stable. The next one is SnF4 is ionic in nature. Similarly, just like here lead, here the tin and the lead are generally like carbon, silicon, germanium, tin and lead. Based on these 14th group elements with the help of chemical bonding properties. That's why read thoroughly chemical bonding characteristics and each and every one synopsis that is correlated with all groups as well as periodic table and some structure of atom points. So based on this silicon, germanium, tin and lead created one question. Ionic and covalent character. That is considered, this question is considered under chemical bonding as well as p block element, that is 14th group family. Now this is ionic also correct. That is the wrong answer is this. This is not a covalent, it is a ionic in nature. Clear. Next one is question number next question is question number 48. Question number 48, this is NEET 2018. Question number 48 in a given assignment. Magnesium react with an element X to form an ionic compound. If the ground state electronic configuration of X is given, the simplest formula of the compound is. Now here the magnesium is react with the X, it forms one compound. What is the formula of the compound? Now in ground state, it's electronic configuration given, that is 1s2, 2s2, 2p3. This is by using this 1s2, 2s2, 2p3. By using this, it is atomic number of nitrogen. This is N. So the nitrogen valency is here. Number of valency electrons are 5, but valency combining capacity is 3. It shows -3. It is fifth or 15th group element. X is. Generally, valency combining capacity is equals to already given 8 minus a group number. Now here the 8 minus 5, that is 3 valency. That's why this X exists as -3. Now here the magnesium is a second group element, shows +2 oxidation state. Magnesium is your second group, that is alkaline earth metal. This alkaline earth metal valency is equals to combining capacity is equals to 2, because its general electronic configuration is NS2. So by using this, Yeah, the Mg plus 2 x minus 3 by crisscross method. They are Mg3x2 is the correct compound. When magnesium is reacted with X electronic configuration given, then obtained compound is empirical formula is very simple. It is related with chemical bonding structure of atom. Okay, so answer is D option. Question number 47. Among calcium hydride, beryllium hydride, barium hydride, the ionic character is just now explained. Ionic character and covalent character. Now you are given question number 47. That is also NEET 2018. NEET 2018. Your calcium hydride, beryllium hydride, and barium hydride given. Now the correct ionic character is increasing or the decreasing order. Now you are the beryllium, magnesium, calcium, strontium, barium are the second group elements, alkaline earth metals. Now its general electronic configuration NS2. Now its valency is +2, +2, +2, +2, +2. Now created from beryllium and from calcium and from barium, taken these three alkaline earth metals. When hydrogen is combined with the same family or alkaline earth metals like lithium or the sodium, potassium, rubidium, cesium, and francium. Now the hydrogen combines with the same family or alkaline earth metals. In this case, hydrogen shows 17th group or 7th A group element characters, halogens. That's what is -1, it is +2. By crisscross method, we'll get BaHa2. Now here -1 +2 by crisscross CaH2. Now here -1 +2, here BaH2, this is. These three compounds given. Here for a given same anion is same, but cation differs. That cation is Ba +2H2. Now here the Ca +2 and H -1 by crisscross method, and barium hydride like here +2. Now hydrogen -1, here -1, here -1. Anion is same, hydrogen, but cation differs. Beryllium, calcium, and barium. According to Fajans rule, and by using polarizing power for cation, your polarizing power Pp is inversely proportional to the size. Size is more, polarizing power is less, covalent character also less. Covalent character decreases. Now your question is the correct order of ionic character. Now this is size of cation is more, covalent character is more, means it is more ionic in nature, more ionic. This is less ionic. So the correct order of increasing order of their ionic character means beryllium hydride is covalent, then covalent character decreases, ionic character increases. Now this is the correct order of ionic character of these three compounds. That's why answer is A. So from ionic and covalent character, recent year 2019 given, 18 given, maybe next year also we can expect one question. And also see the question number 26. Which of the following is a polar molecule? Polar and non-polar, yesterday explained to you. Polar covalent bond is generally formed between two different elements having different electronegativities. Non-polar pure covalent bond is formed between two same same electronegativity elements. Clear? Here, which of the following is a polar molecule? Once we can observe SiF4, XeF4, BeF3, and SF4. Sulfur tetrafluoride is a polar in nature because your question number 26, that is NEET 2013, your SiF4 is generally polar in nature because electronegativity difference is more generally. Now here oxygen sulfur, your fluorine chlorine, it is 16th group, it is 17th group element. Now here top to bottom electronegativity decreases and left to right electronegativity increase. Combination is between these two. Now the sulfur and fluorine, around sulfur 4 fluorine atoms are bonded. Electronegativity difference is more, that's why it is a more covalent in nature, that is polar in nature. So answer is D option. Like some questions based on related concepts, I'll cover it. 4 questions covered based on only ionic character with the help of covalent and ionic compounds. So after some important examples under Fajans rule, one more important point is there. After that, I'll cover formal charge. See here, one more important point about Fajans rule. Generally, compounds with the pseudo-electronic configuration are more covalent than inert gas electronic configuration. Very, very important point. So compounds with the pseudo-electronic configuration. Sorry, your pseudo-electronic configuration is nothing but N-1 D10, your NP6 and NS2 total in its outermost orbit. It contains 18 electrons, that is the pseudo-electronic configuration. Generally, for Cu plus 1, your Zn plus 2 generally having a pseudo-electronic configuration. This is argon 18, your 3D10 4s0 electronic configuration. It also argon 18, 3D10 and 4s0 electronic configuration. Now in this case, argon means here we can write 1s2, 2s2, 2p6, 3s2, 3p6, your 3D10 electronic configuration 18 and 4s0. Now here it contains 18 electrons. Last number is 4, that's why 4 minus 1, 3D10, your 4s6 and 4s2 next. Here also your 3s and 3p6, 3D is in its outermost orbit, 18 electrons are there. Whereas here calcium is there, Ca plus 2, 1s2, 2s2, 2p6, your 3s2 and 3p6 in its outermost orbit. Only 8 electrons are there, that is the octet electronic configuration. So by using this in examination, if they'll ask any one question, which is more covalent in nature, means by using electronic configuration, by using pseudo-electronic and octet electronic configuration, we can easily decide is it covalent or ionic character. For example, your ZnCl2 and CaCl2 is there, two given like, which is more covalent in nature. Here anion is the same, Cl and Cl, but here cation is Zn plus 2 and Ca plus 2. It has 18 electronic configuration, that is pseudo-electronic configuration. That's why it is covalent in nature generally. And here it is 8 electrons, that is octet electronic configuration. This is ionic in nature. So in this manner, by using Fajans concept, we can easily express here nature of compounds, either it is ionic or covalent, increasing order or the decreasing order. Clear. Then next important topic is formal charge. Generally, we know charge, oxidation state, valency, combining capacity. In a redox reaction, we know there how to calculate oxidation number or the oxidation state of each and every one element present in a compound. We know already, according to some important rules and regulations of redox reactions to calculate oxidation states. Here oxidation number or the oxidation states. Oxidation state or the oxidation number. OS or the ON oxidation number. To calculate oxidation state of carbon in CO3 minus 2 ion, some of the oxidation states or oxidation numbers of each and every one element present in a species is equals to their charge, whole charge. Yeah, carbon we don't know, that's why let us consider X. Oxygen is minus 2, general oxide, this is and 3 are there, is equals to their charge is minus 2. This minus is for oxygen. This minus is whole. So sum of their oxidation states of each and every one element present in a ion or molecule or species must be equal to their charge, that is oxidation state of that particular element. Your x minus 6 is equals to minus 2, x is equals to minus 2 plus 6, that is equals to plus 4 oxidation state. So carbon oxidation state in this is plus 4, oxygen is minus 2. This is the way to calculate. For example, in CH4, what is the oxidation state means? Your carbon we don't know, that's why let us consider X. Hydrogen is here plus 1 into 4 is equals to their charge is not there, that's why is equals to 0. Neutral molecule it is equal to 0. X is equals to minus 4 oxidation state. So this is the story about oxidation state. But here in this chemical bonding, one of the most important term is introduced, that is a very, very important concept, formal charge. This formal charge is denoted by QF. Charge means Q, formal charge means F. Formal F, charge Q. Now this formal charge indicate the charge of individual atom present in a species. It also indicate the stability of the species. If formal charge QF is equals to 0, that is more stable. Now generally total formal charge, generally we can calculate total formal charge is equals to sum of the total charge on each and every one atom divided by total number of bonds between two atoms of an element. Now by using this simple important analysis, To calculate the formal charge of each and every one element present in a species, created an important formula, that is QF is equals to the total number of valency electrons minus your total number of LP electrons, that is non-bonded electrons minus 1 by 2 into total number of bond pair electrons, or the bonded electrons. This is the formula to calculate the formal charge. Very, very important. Now here to calculate formal charge, best example I'll take here O3 molecule, ozone. In ozone, how to calculate its formal charge? Here in ozone, 3 oxygen atoms are present. Each oxygen atom atomic number is 8. Its electronic configuration, we know 1s2, 2s2, 2p, 4. In its outermost orbit, 6 valence electrons are there. We know Lewis dot structure is the same. Lewis dot structure of oxygen. Here, 2 paired and 2 are the unpaired. This is the unpaired and unpaired. These 2 are paired. This is the paired nearby each and every one. These 2 are the unpaired. That's why here Lewis dot structure we know by using that Lewis dot structure of oxygen. In ozone molecule, 3 oxygen atoms are there. It is a triatomic, homo-triatomic molecule. We can take like oxygen, here oxygen and oxygen. A rough diagram to write the Lewis dot structure. Now here I'll take here lone pairs here 2, and here I'll take 2 unpairs and remaining these. And I'll take here 2 unpaired. This is the lone pair. And again, I'll take these are 2 lone pairs. Again, these 2 are also, I'll write for this oxygen atom, particularly 1 lone pair. After shifting, it becomes vacant orbital. In this case, your vacant orbital is present. Now this oxygen atom lone pair means this oxygen atom, 1 unpaired electron donated to this oxygen atom, it forms a sigma covalent bond. And again here it donates 1 electron pair like this. Now in these 2 oxygen atoms there exists 1 double bond. Here 1 lone pair is there, here 2 bond pairs are there, and here 2 lone pairs are there. And to get a link between this oxygen and this oxygen atom, this pair is again donated to this oxygen atom. It forms a coordinate because they are vacant orbital. In this case, shifted. It is the structure of ozone molecule. Why sir this bond is here? Why not here? Means we can write like this also: oxygen, oxygen, and oxygen. Here double bond, and here 2 lone pairs, just like. And here 1, and here 3 lone pairs, and here take 1 vacant orbital donated like this. These 2 are called a form 1 and form 2. These 2 are called a canonical structure of ozone. Now the double bond is present between here as well as here. That's why we can take one more important structure, that is called a resonance. Means the double bond is present between these 2 or between these 2. This is called a resonance hybrid structure. What is the resonance hybrid? Very, very important. So the resonance, the resonance hybrid structure, the resonance means the distribution of valence electrons around 1 oxygen atom differ from molecules to molecular structure. The redistribution of valence electrons around one atom of element in a molecule is called resonance structure. None of these structures didn't explain any characteristic of this molecule. Combining all these structures, finally the resonating structure explains its characteristics. Yeah, there is a single coordinate bond, here double bond is present. Here a single covalent bond and coordinate double bond is present. Here a bond length and here a bond length differs, but commonly we can take here and here the same bond length, that is 128 picometer, 128 picometers. Later we'll discuss again some more important points about resonance. First we want here formal charge. Now leave it about resonance. I'll take one example. This is the oxygen atom 1, this is the oxygen atom 2, this is the oxygen atom 3. So the oxidation state means total overall charge possessed by molecule or the species. But here formal charge means your individual atom of an element present in a molecule shows some charge, that is called a formal charge. To calculate this formal charge of oxygen in O3, ozone, or any molecule, or this oxygen atom, formula is this. While calculating formal charge for each and every one atom, always use this formula. Total number of valence electrons of this atom and total number of lone pairs, andre number of lone pair electrons, not a lone pair. Pair is one, don't take one pair. Number of electrons, 2 electrons, minus divided by 2 total number of bond to pair of electrons. How many electrons are participated in bonding? Here 2 bonds are there, here 1 bond is there. Total 3 bonds. 3 bonds means to get the each bond, how many electrons required? 2 electrons required. Total 6 electrons are present. So by using this, for O3 molecule, ozone molecule, formal charge, your formal charge of one first oxygen atom is, here around this oxygen atom, number of valence electrons are 6 are there, minus number of total number of LP, lone pair of electrons, and only one lone pair is there, that's why 2 electrons, minus 1 by 2 into 6 bond pairs are there here. See here bond pairs. Here to get the one bond 2 electrons, here 2 electron, 4 electrons. And this oxygen atom is not donated for sharing. Only this oxygen atom donated 2 electrons to share. That's why one pair only participated. That's why we can use 2 electron. 2 plus 4, 6 here. Now this is 3. 6 minus 2 minus 3, that is 6 minus 5, that is equals to 1, that is plus 1. That is the individual in a molecule, this oxygen atom, individual oxygen atom charge is plus 1. Similarly, second oxygen atom, that is formal charge of second oxygen atom is number of valence electrons 6 only. Here also 6 valence electrons, because it's electronic configuration we know. By using electronic configuration, number of valence electrons are 6. And how many lone pairs are there means here 2 lone pair means electrons are 4. That's why minus 4 minus half into number of bond pairs. How many means here only 2 bond pairs are there. Each pair containing 2 electrons. That's why here 4 electrons. Here 2. 6 minus 4 minus 2, that is 6 minus 6, that is equals to 0. So for this second oxygen atom charge is 0, 0 charge. Third oxygen atom, that is QF3, third oxygen atom, valence electrons are 6. Number of lone pairs, here 1, 2, 3 pairs are there. 3 pairs means 6 electrons are there. That's where the minus 6 minus 1 by 2 into bond pair means only one. These 2 electrons between these 2 and bond is there. For that bond 2 electrons are there. That's why here 2 electrons divided by 2. 1. That is 6 minus 1. 6 minus 7, that is equals to minus 1. Now for this formal charge is minus 1. For O3 molecule, a net formal charge, net QF is total formal charge. Total are the sum of formal charge by total number of bonds. Total number of bonds around the central atom. Already given formula. So the net means total. Total formal charge means for oxygen atom 1 is +1 plus 0 minus 1 divided by around each oxygen atom around is total here 1 bond, here 2, 3 bonds are there. That's why 3 bonds, that is equals to 0 by 3. 0 by 3 is equals to 0. Net formal charge for ozone molecule is, net formal charge is equals to 0. So total net individual atom is +1, 0, -1, but total net charge is equals to 0. In this manner, better you calculate different examples given in our material like CO3 -2. Around carbon atom make like oxygen, yeah, -1 and -1. So each and everyone create as 1, 2, 3, 4 like, or create 1, 2, 3, 4 like this. Each and everyone atom of element, better you calculate formal charge. Now for this carbon valency electrons are 4, but here valency electrons are 6. Oxygen. Element to element changes its number of valence electrons. In all the 3 oxygen atoms in ozone, number of valence electrons are 6 only. Whereas there are 6, but in carbon number of valence electrons are 4. In this manner, better you calculate formal charge. Maybe next year we'll expect one question based on this. Net formal charge or the formal charge of each and every one element present in particular compound. Okay, next. So after this Fajans rule, formal charge. Another important concept is bond parameters. In this bond parameters, 4 important parameters are there for a bond. Bond parameters. Here bond is nothing but here covalent bond, and second one is ionic bond. For this covalent and ionic bonds, here 4 important parameters are there. One is bond length. Second one is bond enthalpy. Third one is bond angle. Fourth one is bond order. General, very simple concepts. Now here the covalent bond, ionic bond, whatever it is. Generally, for ionic bond, like between A plus and B minus, this is the cation, this is the anion. Here the cation distance from nucleus to the positively charged ion. Anion is nucleus to the negatively charged ion. The radius of cation plus radius of anion. This is the radius of cation, radius of anion. Distance is between A plus and B minus distance is equals to sum of radius of cation to the radius of anion. If it is ionic compound, that diameter distance is internuclear distance between A and A. This is the homodiatomic molecule. radius of A plus radius of A, because it is a covalent in nature, covalent compound. It is for ionic. This covalent is homo. If it is heterodiatomic molecule, to calculate the distance between A and B, there is an important formula, that is radius of A and radius of B plus C into XA minus XB. This is the formula to calculate covalent radius, diameter. Here the radius of one atom A and another atom. C is the constant, experimentally determined constant value, particularly for second group, second period elements, that C value is 0.08 constant, and for third period value is 0.06 constant value. This is the electronegativity of A element and electronegativity of B element. By using this, we can calculate the distance or the radius. Generally, this is the distance or the radius expressed in terms of angstrom units, picometer, nanometers. We know values, angstrom, picometer, nanometer values. In this manner, we can calculate. Now, on the basis of this, what is bond length, bond enthalpy, bond angle, bond order? Tomorrow we'll discuss very clearly. Along with this, I'll explain bond polarity. Very, very important. Based on this, we'll create one question in object. Okay. Thank you. Take care.